We're in Rosen, section 1.4, predicates and quantifiers. Again, Rosen, discrete mathematics and its applications. Here are the topics discussed in this section. We will discuss predicates and variables in this video. So propositional logic, while very powerful, is not enough to do the kinds of math that we want to do in computer science or other applications. Here's an example. If we have two statements, they're propositions, all men are mortal, and Socrates is a man, does it follow that Socrates is mortal? Well, certainly it does, and we know that it does intuitively, but we can't make that leap from those two statements to the third statement with propositional logic alone. We have to talk about other aspects of it, such as the objects inside of them and the relationship between the three statements. And then we will have to draw an inference, and we'll learn how to do that later. So the added power that we're going to learn is called predicate logic. So what we're going to add to propositional logic is the concept of a variable. And these are not atomic propositions. These are variables that can take on values from any domain. They could be integers, they could be names of people, they could be types of animals. So these are variables that take on values from a domain. And then a predicate, which is sort of the completion of a sentence, is greater than 3, are equal to each other, is the concept of a predicate. You have a subject, which would be our variable, and then a predicate, which completes the sentence to give us what is known as a propositional function. We can also bind these variables with quantifiers, which we'll cover in the next presentation. All right, so when we take the variables and we combine them with predicates, we get what are known as propositional functions. There's what they're made up of. And we usually designate these propositional functions with a capital letter and then the variables in lowercase as inputs. And then, like I said earlier, variables are replaced by elements from their domain, a set of all possible values they can take on. All right, so when you have a propositional function, it can become a proposition when the variables are given a specific value from the domain, or if we bind them in a sort of set way by quantifiers, which we'll discuss later. And how do we read that? Well, we just like you do any type of real valued function. You say p of x or p at x. It's the value of the propositional function at x. Now, the only possible values it can take on are true and false because it is a propositional function. And here we have a propositional function. We see that as a variable and a predicate. The variable is x, the predicate is greater than 0. And we declare the domain to be integers. Let's evaluate p at x with various values of x. Well, p at -3 is false because -3 is not greater than 0. P at 0 is false because 0 is not greater than 0. And p at 3 is true. We will often use the capital letter U to denote the integers, but the domain. In this case, the domain is integers, but we do have to define the domains for our variables. All right, here's another slightly more complicated propositional function, x plus y equals z, and we'll designate it with r at x, y, and z. And we'll use U, the same domain for all three variables will be integers. Let's find some truth values. Well, if x, y, and z are 2, -1, and 5, is r true? No, because 2 minus 1 does not equal 5, so this would be false. If x, y, and z are 3, 4, and 7, is that true? Yes, because 3 plus 4 does equal 7. And if x, y, and z are x, 3, and z, does it have a truth value? No, because we didn't determine or fix the values of all the variables. So we have a non-proposition. It remains a propositional function, in this case, in only two variables, x and z. All right, here's another propositional function, x minus y equals z, denoted by q. Again, with the integers for all three variables. 2 and minus 1, if x, y, and z are 2, negative 1, and 3, is that a true statement? Yeah, because 2 minus negative 1 is 3. 3, 4, and 7, is q true? No, because 3 minus 4 does not equal 7. And once again, with x, 3, and z, we haven't bound all the variables, so we do not have a proposition. We have a propositional function in x and z. All right, and since these are propositions, when their variables are bound, we can use our connectors to create compound expressions with these propositional functions. P at 3 or P at negative 1. Well, P at 3 is true, and so it doesn't matter whether P at negative 1 is or not, that's going to be true. P at 3 and P at negative 1, well, P at negative 1 is false, so both of them have to be true for this statement to be true, so that's false. And P at 3 implies P at negative 1. Well, P at 3 is true, P at 1 is negative 1 is false, and a truth implying a false is false by our truth table for implication, so that's false. And if we didn't, we can go ahead and connect propositional functions using the connectors. But when we do that, we don't have a proposition. We just have a more complicated propositional function. This first line here, p at 3 and p at y, is just a propositional function in y. And p at x implying p of y is a propositional function in x and y. We'll talk about quantifiers next, about how we can use those to bind the variables in propositional functions. That's another way to create a proposition besides just fixing the values.